Here we discuss in the chapter of atomic structure the conceptual and numerical questions of objective type of all different models of single answer, multiple answer, assertion reason, statement type. The different type of questions especially important in view of MCET examination we are going to discuss. Here at the beginning most of the questions are conceptual questions and then numerical problems also given, which are very useful for the MCET examination in both MPC and BPC streams. So now let's go to questions one by one. Let's go for the question number 1. Now let's see the question number 1. The electric discharge through gases in cathode ray discharge tube was observed at the discharge tube experiments, or this is a discharge tube where gas at very low pressure, gas is taken at a very low pressure and it's applied to a high voltage. This is anode and cathode. So this is at a very high voltage current. This is about 10,000 volts, and low pressure it's about 1 mm of mercury. Then when such a high voltage current is applied to at a very low pressure basically means very small amount of gas is taken to a very small amount of gas. When certain high voltage is applied, the gas will ionize and the radiations that are obtained when the discharge tube starts glowing, the glow is observed when such a high voltage is applied. So this is what is actually Rutherford's discharge tube experiments. So in this, a gas is taken in a discharge tube at very low pressure and high voltage. So very low pressure and high voltage is the correct answers. So the answer is option number 1. The question number 2 says charge to mass ratio of the electron is. Electron is a negatively charged particle revolving around the nucleus. It carries a charge of 1.6 into charge of the electron is 1.6 into 10 power minus 19 coulombs, and mass of electron is about 9.1 into 10 power minus 31 kg. So the question is that charge to mass ratio. Charge to mass ratio, this is what we call E by M ratio. E is for the charge, M is for the mass. E by M ratio means charge to mass ratio, or this is also what we call charge density, specific charge. E by M ratio, or this is called specific charge. So this is the E by M ratio 1.6 into 10 power minus 19 coulomb by 9.1 into 10 power minus 31 kg. So it is coulomb per kg, and if you divide this, then you will get the answer as about 1.75 into 10 power 11 coulomb per kg. So this is the answer. So the correct answer is option 2. Now let's go to question number 3. Now in the question number 3, the question is what is the frequency of radiation whose wave number is 6000 centimeter inverse. Wave number nu bar is equal to 6000 centimeter inverse. So in the question number C, it is given that what is the frequency of radiation whose wave number is 6000 centimeter inverse. Wave number nu bar is 6000 centimeter inverse. The frequency of the radiation. Here frequency of the radiation, here we have different formula. Energy is equal to h nu, or this is equal to hc by lambda, or this is equal to 1 by lambda is what we call frequency. So this is wave number h c nu bar. This is how we have the relation for wavelength, frequency, wave number and energy of radiation. So finally nu is equal to c by lambda, and 1 by lambda is nu bar. So it is nu into nu bar. Now nu bar is given. So then when nu is equal to c into nu bar, so nu is equal to c, that is velocity of light, 3 into 10 power 10 centimeter into nu bar given is 6000 centimeter inverse. So now this if you multiply, now we will get it as, now this is 1.8 into this is 1.8 into 10 power 14. So frequency is 1.8 into 10 power 14 second inverse. So the correct answer is option 1. Now let's go to question number 4. Now the question number 4 says the wavelength of electromagnetic radiation of frequency 10 power 3 kilohertz is. This is again somewhat similar to the previous question. Here it is the relation conversion of frequency into wavelength. Here nu is equal to c by lambda. This is what the relation between frequency and wavelength. Now frequency is given as 10 power 3 kilohertz, means 10 power 6 hertz, 10 power cycles per second. 10 power 6 is equal to 3 into 10 power 10 by lambda. So from this lambda is equal to 3 into 10 power 10 by 10 power 6. So this comes out to be about 300 meters. So this is comes out to be 3 into 10 power 4 centimeter. So lambda is equal to 3 into 10 power 4 centimeters, which is equal to 300 meters. So the correct answer is option 3. Now let's move to the question number 5. In the question number 5, it is purely conceptual question. 6C14 and 7N14. They are the two nucleides of isotopes of 6C14 is isotope of carbon, 7N14 is isotope of nitrogen. Now 6C14 and 7N14. These are the nuclei of two different elements having same mass number. Nuclei having same mass number but different atomic number. Here mass number is same for both, it is 14. Atomic number is different, 6 and 7. So these are said to be isobars. Isobars are the nuclei having the different mass number, same mass number and different atomic number. Whereas isotopes are nuclei having same atomic number but different mass number. So here the correct answer is isobars, that is option 1. Now let's move to the question number 6. This is again a conceptual theoretical question. Rutherford's experiment, which established nuclear model of atom, used a beam of. In the Rutherford's experiment, in the gold foil experiment, alpha rays have been polonium source. Alpha rays are impinged on a metal surface, and some of the rays have been deflected, some of the rays have been passed through, and some of the very few of them are completely reflected back. From this experiment, the structure of the atom is tried to understand. Now basically, so now this question relates to a model of an atom, which beam is used. So it is the alpha particles which impinged on a metal foil and got reflected is the concept over here. Alpha particles from a polonium source are incident on a metal surface. Some of the alpha rays are found to pass through the metal foil, and some of them scattered at certain angles, and very few of them are reflected back. So the correct answer here is option 1. Now let's move on to the question number 7. Which one of the following elements has non-spherical orbital for the electron? Non-spherical orbital for the electron. Normally when electron means here the valence electron. Helium configuration is 1s2. So the electron is in the s orbital. Boron atomic number 5 has the configuration 1s2, 2s2, 2p1, where p orbital is a non-spherical dumbbell shaped orbital. So that is a non-spherical orbital, whereas beryllium atomic number 4, it is 1s2, 2s2. The electron is in the s orbital, which is spherical. Lithium atomic number 3, configuration 1s2, 2s1. So that is also in the s orbital, that is spherically symmetrical or spherical orbital. But boron, that is 1s2, 2s2, 2p1 with atomic number 5. The valence electron is in the dumbbell shaped p orbital but not spherical shape. So the correct answer is option 2. So in the question number 8, this is again a conceptual question. This is regarding the black body radiations. Here it says a hollow sphere coated inside with platinum black. A hollow sphere coated inside with platinum black. When this is heated to, this is what we call a black body, a black colored hollow sphere coated inside with platinum black and has a small hole. This is a small hole. In it is nearly a black body. This is what is called nearly a black body. What is the reason to be called as a black body? Because on heating, what it does is it not only absorbs, here it absorbs all radiations upon heating, and all that whatever it is absorbed, all the radiations, again all the radiations are emitted back. So this is what is called black body. Any body which not only absorbs all radiations in the sense radiations of all wavelengths and frequencies, if it absorbs as well as if it emits, then we call it as perfect black body. So here it emits and absorbs all frequencies of radiation is the correct answer. So the correct option is option number 4. Question number 9, what it reads is the hydrogen spectrum consists of several series of lines. Then which one of the following equation expresses spectral lines in terms of frequencies in hertz, where RH is the Rydberg's constant. What the Rydberg constant is, when electron transitions takes place between different energy levels, then these are the electron transitions. To find the wave number, wavelength and frequency, Rydberg has given an equation according to which nu bar equals to 1 by lambda equals to RH into 1 by n1 square minus 1 by n2 square, where n1 is the lower energy state to where the electron transition takes place, and n2 is the higher energy state from where the electron transition being taken place. RH is a constant, where RH is equal to 109,677 centimeter inverse, and here the question is with respect to the nu, and as we know that nu is equal to C into nu bar. So this is equal to C into RH into 1 by n1 square minus 1 by n2 square is the correct answer. So in the given options, the correct answer is C into R into 1 by n1 square minus n2 square, that is option number 2 is the correct answer. Now let's move on to the question number 10. The question number 10 is a conceptual question where it is asked about what is the value of Rydberg's constant. The Rydberg constant, as we have written it over here, this is the value of the Rydberg constant, where it is 109,677 centimeter inverse. So the correct answer is option 2. Now let's move on to question number 11. Splitting of spectral lines under the influence of external electric field is called. Here this is with respect to the, while determining the orbitals, then while studying the atomic structure, it was observed that when an atom is subjected to a certain electrical and magnetic fields, then there is a splitting of spectral lines observed in the spectra. Here this splitting in electrical and magnetic fields were observed by Stark and Zeeman respectively. First, the splitting of spectral lines under the influence of external electrical field is observed by Stark, and the splitting of spectral lines in external magnetic field is observed by Zeeman. So these effects are called Stark effect and Zeeman effect. In this question, it is given the splitting of spectral lines under the influence of external electric field. So it is a Stark effect. So the correct answer is option 4. Now let's move on to question number 12. In the question number 12, it is asked the necessary condition to get an electron wave in phase. So suppose if this is the nucleus and this is the spherical orbital according to Bohr's theory, but according to de Broglie's concept, as electron is having a wave nature, now this is the wave nature. Now for this electron to be in same phase means after one complete revolution for electron to follow the same path. That is the meaning of the question. For electron to continue in the same path, that means for an electron wave to be in phase, that means when both have to be on same phase, means meeting at same point, then what is the necessary condition? The necessary condition is that the circumference of the electron orbit, that is this, right, 2 pi r, is equal to integral multiple of the wavelength. This is what in the de Broglie's equation what we will say, 2 pi r equals to n lambda. So 2 pi r, that is the circumference, must be equal to, if this wavelength is lambda, this is the wavelength lambda, then wavelength lambda and these are the number of waves. So this is the wavelength. When this is the wavelength and you have n number of waves, so circumference is equal to number of waves into wavelength. So 2 pi r is equal to n lambda. So the correct answer is option 1. Now let's move on to question number 13. Now to the question number 13. One of the important consequences of uncertainty principle. What is uncertainty principle? This is what in general we call it as Heisenberg's uncertainty principle. What Heisenberg's uncertainty principle says is that for a fast moving particle like electron, the position and momentum of electron cannot be determined simultaneously and accurately. If an electron is moving with a momentum p and at a position x, then that x and p measurements, if we do simultaneously, that result will not be accurate. There will be some uncertainty associated with both the measurements, and that uncertainty in position, if you take it as delta x, and uncertainty in momentum, if you consider it as delta p, then according to uncertainty principle, the product of uncertainties of velocity or momentum and position is greater than or equal to delta x into delta p is greater than or equal to h by 4 pi. Okay, so one of the important consequences of uncertainty principle. So what actually we understand from this? What actually we understand from this is that electron cannot revolve around the nucleus at a definite, particularly exactly known path. There will be certain disturbances, there will be some deviation. So uncertainty principle does not agree to accept that the electron revolve in a definite path. So it rules out the existence of definite paths for the electron. That's what the uncertainty principle says. So here the correct answer is option 2. Now let's move on to question number 14. The acceptable solutions of wave functions of the Schrodinger's equation are. This is a purely conceptual, just like a definition it is. The acceptable solutions of wave functions of Schrodinger's wave equation. Schrodinger's wave equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square e minus u is equal to 0. This is what the Schrodinger's wave equation is. Now this is a second order differential equation. It will have many solutions, but all solutions are not acceptable as they suffer with certain boundary conditions. Those solutions which satisfy all the boundary conditions, here we have certain boundary conditions like the wave function must be normalized, the wave function must be continuous, and the wave function must be single valued. Like this we have certain conditions. So those solutions which satisfy all these conditions for this psi, so this second order differential equations, psi will have many solutions, and in that whichever are the acceptable, those solutions are what we call eigen wave function. So this psi xyz is what we call an eigen wave function. So here the correct answer is option 1. In the question number 15, the state of an electron in space represented by psi xyz, the probability of finding an electron at a point in space is given by. So here, as in the Schrodinger's wave equation, as we gave the wave function psi xyz in the previous question, that what we gave, if we gave an eigen function as psi xyz, then probability of finding an electron, probability of finding an electron is what we give it as psi square xyz. If psi xyz is a wave function, then psi square xyz is probability of finding the electron. So the correct answer is option 2, psi square x y z. Now in the question number 16, this is again related to Schrodinger's wave equation and wave mechanics. In this the question asked is, which one of the following is a radial probability distribution function? Radial probability distribution, that is about the distribution of electron density at different radial distances from the nucleus. If the radial distance is r, if this is the nucleus, then at a distance r, what is the distribution of electron density from this? This is a mathematical equation based on that second order differential equation what we give in this Schrodinger's wave equation. That if we take into consideration, then this 4 pi r square dr into psi square, where psi square is a probability of finding an electron, 4 pi r square dr is a change in the radial distance. So with change in a small radial distance dr, what is the change in electron density? That is probability of finding an electron. So that will be 4 pi r square dr psi square. So the correct answer is option 3. Now let's move on to question number 17. In the question number 17, what it says, the number of peaks appearing in the radial distribution curves drawn for s orbital is equal to. Now for any electron, first of all, radial probability distribution curves, so d function, that is d is equal to 4 pi r square dr psi square, and this is the radial distance r. The curves what we will get is either suppose if it is n is equal to 2, then you will get the curves like this. For n is equal to 1, so it is dependent on the values. Number of peaks is equal to, this is for 2s. If it is for 1s, then you will get the curve like this. For 3s, you will get the curve like this. This is for 3s. This is for 1s. For 1s, you will get 1 peak. For 2s, you will get 2 peaks. For 3s, you will get 3 peaks. So number of peaks is equal to value of n. N is equal to 2 peaks. N is equal to 1 peak. N is equal to 3 peaks. So the number of peaks in radial probability distribution curves is equal to principal quantum number n. So the correct answer is option 1. Now let's move on to question number 18. The question asked is the number of radial nodes for any orbital. Radial nodes means radial distance. If you suppose if you have 1s, 2s, 3s like this. Now this is the nucleus, this is your 1s, 2s, 3s, like this when you have, then at this distance what you are having, here the electron density increases and at some stage it will become 0 and then it increases. It will be from the nucleus as you move, initially here it is 0, it will increase, then decrease, here it will become 0, then again it will increase, here it will be maximum, again it will decrease, here it will become 0, again it will increase, so on and so forth. So it all depends on which orbital to which energy shell. If it is 1s, this is 1s, here you will not have any such spherical node. This radial node otherwise is also called spherical node. 1s doesn't have any spherical node, but when it comes to 2s, you have one spherical node. So here the number of spherical nodes is given by n minus l minus 1. For 1s, it is 1 minus 0 minus 1, that is 0. For 2s, it is 1 minus 2 minus 0 minus 1, that is 1. For 3s, it is 3 minus 0 minus 1, that is 2. And for 1p we don't have, 2p, then we have 2 minus, for p l is equal to 1, 1, that is 0. For 3p, it is 3 minus 1 minus 1, that is 1. So like this, finally number of radial nodes is equal to n minus l minus 1. So the correct answer is option 4. Now in the question number 19, the value of probability density function on the plane where the two lobes of p orbital touch each other is. So, this basically it relates to nodal plane. What is a nodal plane? Nodal plane is nothing but a plane passing through origin, passing through nucleus, origin means nucleus, where psi square is, that is probability of finding an electron is 0. So, the question is not that the plane probability density function and the plane where the two lobes of p orbital. So, the two lobes of p orbital are meeting at a here. So, this is nothing but, so this is about this plane. If you take this particular plane, here psi square is 0. This is a plane passing through the nucleus where the probability of finding the electron is 0, because the entire electron density is over here and is over here. But in this plane, probability of finding an electron is 0. How many? That the value of probability density. So, that is psi square value. What is the psi square value along this plane? Psi square value along this plane is equal to 0. So, the correct answer is option 2. Now, let us move on to question number 20. The common azimuthal quantum number L for all the p orbitals is, for all the p orbitals, if azimuthal quantum number L is equal to 0, that is s orbital, L is equal to 1, that is p orbital, L is equal to 2, d orbital, L is equal to 3, it is f orbital. So, the common azimuthal quantum number for all the p orbitals is 1. The number of the azimuth, if principal quantum number is n, then azimuthal quantum number will be from 0 to n minus 1. So, 0 to n minus 1, this is what the L value. So, this L will take from 0, 1, 2, 3, etc. L is equal to 1 indicates that the electron is in the p orbital. So, the correct answer is option 2. In the question number 21, it is the common azimuthal quantum number L for all the d orbitals. In the previous question, we had similar question, the common azimuthal quantum number for p orbital. There already we told that if L is equal to 1, then it is p orbital. If L is equal to 2, it is d orbital. So, the answer is option 3. Now, let us move on to question number 22. What the question number 22 says? The number of angular nodes for an orbital is equal to number of angular nodes. Its number of angular nodes is nothing but also we called nodal planes. S orbital being spherically symmetrical. First of all, what is a nodal plane? As in some of the previous questions that already I told, nodal plane is a plane passing through nucleus where probability of finding electron is 0. A plane passing through, suppose if you have an s orbital, for an s orbital you will not have any plane, any cross sectional, any plane that you take, you will not have any plane where the probability of finding electron is 0. So, for s orbital the number of nodal planes is 0. But if you have a p orbital, if this is your p orbital, if you consider that this is x axis, then your electron density is mostly concentrated on xy plane and xz plane. But then if this is your x, y and z, then yz plane, this yz plane is the one where probability of finding an electron is 0. So, for p orbital you will have 1. Like this, if you keep continuing for d orbital you will have 2, and for f orbital there is likely to be that they will have 3. All this if you try to recollect, 0, 1, 0 for s, 1 for p, 2 for d, 3 for f. This numbers indirectly is nothing but equal to azimuthal quantum number of that particular orbital. So, the number of angular nodes is equal to the azimuthal quantum number of the orbital. So, here the correct answer is option 2. Now, in the question number 23, it is the sum of radial and angular nodes for any orbital is equal to. Now, as in number of spherical nodes, which is nothing but otherwise called as we told radial nodes, is equal to n minus L minus 1, and number of angular nodes angular nodes, which is nothing but also we call nodal planes. This is equal to L. Therefore, total number of nodes, total number of both spherical and angular, total number of nodes is equal to n minus L minus 1 plus L, that is equal to n minus 1. So, the correct answer is option 2. Now, let us move on to question number 24. The question number 24 says, in a main energy level with a principal quantum number n, the total number of electrons that can be accommodated is, if we have a principal quantum number n, then with the principal quantum number n, number of orbitals is n square, and each orbital will have 2 electrons. So, number of electrons is 2n square. So, the correct answer is option 3, 2n square. Now, let us move on to question number 25. A body of mass 1 milligram is moving with a velocity 1000 meters per second. Mass is 1 milligram is moving with a velocity 1000 meters per second. The wavelength of de Broglie wave associated with it is, according to de Broglie's theory, lambda is equal to h by mv, where h is a Planck's constant which is equal to 6.625 into 10 power minus 31 kg per meter per second, and mass is 1 milligram. 1 milligram means in kg it is 10 power minus 6 kg into velocity 1000 meters per second. So, lambda is equal to Planck's constant 6.625 into 10 power minus 34. Mass is given as this is 10 power minus 34 kg meter per second. This is Planck's constant, and mass is 1 milligram. So, we have to write it in kg, that is 10 power minus 6, and velocity is of course 1000 meters per second. So, when you do this, you will get this as 6.625 into 10 power minus 31 meters. So, the correct answer is option 2, that is 6.63 into 10 power minus 31 meters. Now, let us move on to question number 26. In the question number 26, this is based on again the uncertainty principle, Heisenberg's uncertainty principle. If uncertainty in position and momentum are equal for an electron, the uncertainty in its velocity is, so here delta x into delta p is equal to h by 4 pi equation if you take, then delta p is nothing but m delta v, because p is equal to mv. So, delta p is equal to m delta v, mass is constant, so delta p will be m delta v. Therefore, delta x into m delta v is equal to h by 4 pi, or delta x into delta v is equal to h by 4 pi m. Now, the question is uncertainty in position and momentum are equal, then uncertainty in velocities. So, here what it is given is delta x is equal to delta p. When delta x is equal to delta p means what we can write is delta p square is equal to 4 pi. Then delta p whole square means m square delta v whole square is equal to h by 4 pi, is equal to h by 4 pi. So, from this delta v square is equal to h by 4 pi m square. Therefore, delta v, that is uncertainty in velocity, is equal to root over h by 4 pi m square. This is equal to, this is 1 by 2 m, 1 by 2 m is this, root over h by pi. This is the answer. So, 1 by 2 m into root over h by pi, that is the correct answer is option 3. Now, let us move on to question number 27. The question number 27 is related to quantum numbers. How many electrons in a given atom have the set of quantum numbers n equal to 3, L equal to 2, m equal to plus 2 and s equal to plus half? Whatever may be the values of the quantum numbers, whether it is n is equal to 3 or n is equal to 4, L is equal to 2 or L is equal to 1, M is equal to plus 2 or minus 2 or 0, whatever it is, S is equal to plus half or minus half. But what our principle says is that the Pauli exclusion principle says no two electrons in same atom can have all 4 quantum numbers same. Any 3 quantum, the first 3 quantum numbers, that is principal quantum number n, azimuthal quantum number L, magnetic quantum number m. These 3 can be same for 2 electrons in an atom. But when those 3 are same for 2 electrons in an atom, then S will be different for those 2 electrons. So the meaning is that no 2 electrons can have all 4 quantum numbers same. Same set of quantum numbers cannot be given to any 2 electrons. For 2 electrons, either n may be different, or L may be different, or M may be different. But if all 3 of them are same for 2 electrons, but at least they will differ in their S value. So one set of quantum number is applicable only to 1 electron in an atom, definitely not more than 1. So the correct answer is option 3. Now let's move on to question number 28. Now the question number 28 says, for particles having the same kinetic energy, the de Broglie wavelength is, this is again on de Broglie's wave concept. De Broglie's wavelength is. So here it is lambda is equal to h by mv, and if you convert this in terms of kinetic energy, you can write lambda is equal to h by under root 2 m ke, that is kinetic energy. For 2 particles, if the kinetic energy is same, what it says, for particles having the same kinetic energy, de Broglie wavelength is inversely proportional to velocity, independent of velocity, directly proportional to velocity, or independent of velocity and mass. So is equal to the here, because kinetic energy is nothing but half mv square, right? So if you have lambda 1 and lambda 2 for 2 different particles, if the kinetic energy is same, then because this is half mv square, so this will be 1. So here the correct answer must be that the de Broglie wavelengths, this lambda. So this lambda is equal to h by under root 2m ke, that is under root 2m into ke, that is half mv square, right? So this is, if you take this, so this comes out to be m square v square. So this is nothing but, once again, h by mv. So it's finally it's inversely proportional to velocity. So the correct answer is option 1. Now let's move on to question number 29. This is related to electronic configurations of elements. It's again an important question. What it says is the electronic configuration of Cu2 plus. First of all, copper, atomic number 29. For copper with atomic number 29 and chromium with atomic number 24, we have some exceptional configurations. Copper with atomic number 29 has the valence electron configuration of 4s1 3d10. This is valence electronic configuration for neutral copper atom with atomic number 29. Cu2 plus means removing 2 electrons. Then the configurations, first the electron goes from here and 1 electron from here. So then the configuration changes to 3d9. 2 electrons have to be removed. 1 electron should be removed from the 4s. 1 more electron if you remove from 3d, then it will become 3d9. 4s0, 3d9. So the correct configuration for Cu2 plus is argon 3d9. So the correct answer is option 4. Now let's move on to question number 30. Now what the question number 30 says is, Bohr's radius for hydrogen atom n is equal to 1 is approximately 0.53. The radius of the first excited state, that's n is equal to 2 orbit is. So here radius of nth orbit according to Bohr's theory is 0.529 into z square by n square angstroms, where n is the number of the orbit and z is atomic number. And here because it is given for a hydrogen atom, z is equal to 1. So Rn is equal to 0.529 by into n square by z square. So it is into n square. 0.529 into n square by z square. Z is equal to 1 for hydrogen. So Rn is equal to 0.529 n square. Now first excited state, and that it is given n is equal to 2. So if n is equal to 2, then Rn is equal to 0. This is approximately in the question it is given 0.53. So it is 0.53 into n square, that is 4, which comes out to be 2.12 angstroms. So the correct answer is option 3.